The James Webb Space Telescope is now 1 million miles from Earth and performing science operations. The Nancy Grace Roman Space Telescope is scheduled to launch by 2027. These two observatories are NASA's latest flagship missions in the tradition of Hubble, Chandra, and Spitzer. But why do we need both? And why do they look so different? The answer to both questions is that they are built to do different things. Webb has the exquisite sensitivity and wavelength range to capture detailed images deeper into the universe than ever before. Roman has an incredibly wide field of view to rapidly survey huge areas of sky while still rivaling Hubble and Webb's resolving power. Webb will tell us about the early universe, and Roman will help us understand how it evolved from there. One of the keys to Webb's sensitivity is its huge mirror. At more than 21 feet wide, it's the largest mirror that has ever flown in space. By using such a large mirror to collect more light from faint objects and observing in infrared wavelengths, Webb will peer deep into the distant, early universe. The universe's expansion stretches light traveling through space, a phenomenon called redshift because the light waves we receive from receding objects are stretched to longer, redder wavelengths. Webb is designed to see this redshifted light so that it can study the first, most distant galaxies. The Roman Space Telescope, on the other hand, isn't trying to see quite as deep into the universe's history. Roman does have filters to see infrared light, but not as far into the range as Webb because its targets aren't as redshifted, and Roman's mirror can be smaller because it isn't trying to detect such faint objects. That wavelength difference affects another very visible feature of the two spacecraft. Webb observes light near the same wavelengths that the spacecraft itself would emit if it were not cold. As a result, Webb has a very robust system, including the multi-layer sun shields, to keep it extremely cool. Roman, on the other hand, needs far less cooling because it will observe in wavelengths unaffected by a warmer spacecraft, so the shade provided by its solar panels alone does most of the work. While Webb will peer with intense focus at very specific objects and regions, Roman is a survey telescope designed to capture vast swaths of sky. But it will do so with revolutionary precision, sensitivity, and depth. The key to doing this is the heart of Roman's wide-field instrument, a massive camera with 18 next-generation detectors. Each one captures a 4,000 by 4,000 pixel image, and together they will take pictures covering 100 times more sky than either Hubble or Webb. This wide view will allow Roman to study enough large-scale structure of the universe in high precision for scientists to begin understanding its true nature, including dark energy and dark matter, and viewing early galaxies as a population rather than a few individuals who may or may not be average. Both telescopes will also help us learn more about planets outside our solar system, called exoplanets, but in very different ways, with Roman finding more that were previously undetectable, and Webb gathering new details on those already discovered. These two telescopes, with their different but complementary goals and strengths, will help us understand much more about the early days of the universe, how it has evolved since then, and what other worlds might be out there. The Nancy Grace Roman and James Webb Space Telescopes have very different approaches to studying the universe. Roman has an extremely wide view to capture as much of the cosmos as possible. Webb will peer deeper than any telescope before it to see more detail and farther into the past. These contrasts enable different science and help us answer separate questions about the universe. Beginning with its beginning. Webb will see galaxies that are extremely far away, whose light was emitted when the universe was very young. It will reveal an early universe that scientists have only explored through calculations. We have very little information about the cosmos' infancy, and Webb will help us fill in many of the gaps by making direct observations of galaxies as far into the past as physically possible. Roman, on the other hand, will use the power of its wide sky coverage to survey massive regions of space, documenting significant portions of the universe through its adolescent and early adult years. Not only does Roman have a field of view 100 times larger than Webb's, but its compact and rigid design makes it more nimble, able to quickly repoint that wide view to survey large regions through a process called tiling. Roman will be able to survey thousands of square degrees of sky during its primary mission, enabling studies that were never possible before. Only by studying millions of galaxies can scientists begin to determine the behavior of the universe as a whole, like its large-scale structure and how it has changed over time. Dark matter and dark energy are both large presences in the universe that are only detectable through their effects on normal matter. The brightnesses of faraway supernovae work to measure the distances of galaxies and how dark energy is pushing them apart. The precise shapes of galaxies serve as a way to study the dark matter around them, but these features must be measured very accurately to be usable. Roman's hardware is particularly precise and well understood, so the data it collects is especially good for the statistical analysis required, giving scientists a holistic view of how dark matter and dark energy exist and affect the visible universe. Previous great observatories, Hubble, Chandra, Spitzer, and Compton, greatly expanded our understanding of the universe. Some of it was in ways that scientists and engineers had anticipated and designed the telescopes for. But many other discoveries were unanticipated, as the great observatories revealed new aspects of the universe and scientists discovered creative ways to use these powerful tools. The same will be true of both Roman and Webb. We can anticipate some of what they will show us, but many of the most exciting discoveries are the ones we can't predict. The same capabilities that make the James Webb and Nancy Grace Roman Space Telescopes such powerful tools for studying the early universe will also help them in another key mission, the search for and study of exoplanets, or worlds outside our solar system. Roman's ability to survey huge areas of sky with high precision gives Roman a unique ability in hunting for new exoplanets. Exoplanet missions like Kepler and TESS have been extremely successful at finding exoplanets through the transit method, where planets block some of their host stars' light as they orbit past. But this method is limited in the systems it tends to find. Roman should find thousands of planets through transits, but will mainly hunt for smaller exoplanets with larger orbits using a method called gravitational microlensing. When a planetary system passes between us and another star, the gravity of the nearer star and its planets bends and temporarily magnifies the background star's light. This even works on so-called rogue planets, untethered to any star. Microlensing events are very rare, but Roman's sky coverage will enable it to see many. Roman also has a coronagraph technology demonstration instrument. Its primary goal is to test cutting-edge hardware for the first time in space. At its simplest, a coronagraph uses a disk to block the direct light of a star in order to better see what is around it. Roman's dynamic coronagraph will use special masks, filters, and deformable mirrors to actively sculpt the light, rather than simply block it, giving finer control over reducing the star's glare. This control should allow Roman to directly take actual pictures of planets similar to Jupiter. Webb is equipped with a static coronagraph, and along with its increased resolving power and sensitivity, Webb has a powerful suite of tools to study the light coming from exoplanets, whether radiating as heat from their surfaces, bouncing off them, or passing through their atmospheres as they orbit in front of their stars. By studying this light, scientists can see what wavelengths were emitted, reflected, or absorbed. Even if the planet itself isn't visible as an object, its light can tell us a great deal about what it might look like if our equipment were sensitive enough. Because of this ability, Webb will be our prime tool for carefully studying the exoplanets we have found. The continuing discovery and study of exoplanets, some with liquid water and some which are Earth-size, brings us closer to understanding the conditions necessary for life and where it might exist elsewhere in the galaxy. Roman will expand our catalog of known worlds, and Webb will add detail to many entries within that catalog.
Together, they are poised to make some of the most important planetary discoveries of our lifetime.
The James Webb and Nancy Grace Roman Space Telescopes are two missions with different but overlapping science goals. Both will help us understand the history of the universe and what other worlds exist in it now. They will bring us closer to answering fundamental questions like where do we come from and are we alone? No one telescope can make all the observations necessary to potentially answer these questions, so NASA and its partners have created several. Roman and Webb will be together not just in spirit, but also in their location in space. Both spacecraft will orbit a special place called Sun-Earth Lagrange Point 2, or L2, where the gravitational pull of the Earth and Sun reach equilibrium. Located 1 million miles beyond Earth's orbit, a satellite at L2 orbits the Sun, with Earth's gravity providing an extra tug to help it stay even with the planet. The advantage of orbiting L2 is that both spacecraft will be far from any interference of Earth, the Moon, or other spacecraft. Their orbits are huge, keeping them well away from each other or any other spacecraft at L2. It's colder there, critical for infrared observations. And they never have Earth blocking most of their view. Hubble, orbiting only 300 miles above the ground, has more limitations on where it can point at any given moment. Because both telescopes will operate at the same time, they can work together to discover far more about the cosmos than either could learn alone. When Roman makes an intriguing exoplanet discovery, Webb may be able to follow up soon after, helping scientists learn more. When Roman detects a transient event, like a supernova, somewhere in its broad coverage, Webb can focus in to take deeper measurements. Should Webb find an interesting quirk in a nearby galaxy it's studying, Roman can provide context with thousands of galaxies around it. Using the two telescopes in concert, both with unprecedented but different capabilities, scientists will be able to make more and faster progress than if only one telescope operated at a time. Two of the greatest space telescopes ever built will work together, using each other's strengths to advance our knowledge of the universe.